Hello.
Yes.
Yeah. Actually, I'm traveling today, so I'm on phone, attending from phone,
So you are attending in?
attending in my phone. I'm not having
Okay.
laptop,
Oh,
so
okay. Oh,
I'll not
oh,
be able
thank you.
to admit
Okay.
anyone if they are actually coming up. It won't show for me.
I think people can join now by themselves. I have made
Okay.
the
Okay.
setting such that they can join and leave anytime they want
Okay.
without
That would be
doing
nice.
anything. Yeah,
Yeah.
because sometime NPTEL people join to inspect.
Okay. Okay.
Yeah. Yeah, I will wait 2-3 minutes and then we'll start.
Sure. Then we can start.
Yeah.
Shall we start?
Yes, yes, I will start. I will just
I think it's five
experiment.
three. Okay.
Yeah, I'm not sure why it is not expanding. Just give me a minute, so I will just try once more. The screen should look
Can
bigger.
you make the background? Is it possible to make the background white? Because
Uh,
sometimes when you're writing with blue ink, it's not visible.
Okay.
Red ink is still okay, but when it goes to blue, it's slightly blurred. Maybe the my internet resolution is the issue.
Okay, okay. Okay, okay. Okay. Let's see. I
Thank
will
you.
try again. Mm. Is it fine? No, I made it white.
Yeah, white.
Mm.
White is any light color is fine. White is perfect.
Okay. So yeah, I think we did some mistake in the notations and in the direction negative and positive. So let's see what I was when I was explaining. This is the fourth order CDS. Okay. Okay. Mhm. Okay. So yeah, while saying something, I did something wrong, but okay, we can correct today. So let's see. Let's say I'm solving this dou u by dou t plus c dou u by dou x and equal to 0. And if I am discretizing in time and space, so ut plus 1 and u I minus ut by delta t at I plus c. Let's say I am saying this is a forward differencing, then it will become ut I plus 1 minus uti divided by delta x is equal to 0. So if it will become ut plus 1, this has been multiplied, so it will become uit plus, so this will become right hand side, so it will become minus c delta t by delta x, and it will become ui plus 1 t minus uit. Okay, now if you remember, when we were using this dou u by dou x as a backward difference, uh, so like something like this part, we used to have this negative artificial viscosity. Now, since we have the negative term here as well, so we will be getting some positive artificial viscosity. Okay, and this k is basically, and this is the order of delta x. Okay, first order accurate. Okay, and they are the second order term. No, I mean sorry, into delta x. Okay, now this is the term that is okay. We can directly remove it for now. So this is a term that looks like a viscosity. Okay, if we will be doing this backward difference. Okay, okay, sorry. So this is a forward difference, right? So we will get the negative value here. If we will be using the backward difference, uit plus 1 is equal to uit minus c delta t by delta x ui t minus ui minus 1 t. Okay, and then we will get something k day square u by dou x square. Okay, and in this case, our c is positive. And remember that k contains the c. So like some k, and k is basically a into c. Okay, like a is some other coefficient that is coming from there. Okay, similarly here. K is basically A into C. Okay. Now look into this. If C is greater than 0 in dou u by dou t plus C dou u by dou x equal to 0, and if C is greater than 0, in that case, for the forward difference, we will get the negative artificial viscosity. Okay. And if C is greater than 0 and the forward difference, we will get negative artificial viscosity. And for the backward difference, we will get the positive artificial viscosity. If C is less than 0, then for the forward difference, we will get the positive artificial viscosity. And for the backward difference, we will get the negative artificial viscosity. Okay. This is the mathematical thing. Okay. Let's take little bit the let's take some understanding, the physical understanding of how this is going to create problem or become convenient for us. Like let's say when we say C is greater than 0 and we are solving 1D problem, that means our wave is moving in the positive direction. Okay, this is the direction of wave. This is the velocity of the wave. Okay, and in that case, let's say these are my stencils, basically the discretization. And if we are saying that dou u by dou x is ui plus 1 minus ui by delta x, that means, and let's say into C as well. So that means we are saying that when we are trying to calculate at ui, this is I, and this is ui plus 1, like at any time t, we are like calculating at the I, right? We are getting the solution at I, at t plus 1, right? So at I, we are trying to get the solution from the upstream. Like when we are moving in this direction, then this is called the downstream. Sorry, when we are moving in the positive direction, then this has become the downstream, and this has become the upstream. Okay, this is the like nomenclature. Just have understanding, like in which direction we are going. That is the downstream. Like when you are moving from top hill to the bottom is basically the downstream. In which direction the water, let's say if there is a water flowing, then basically water is flowing the downstream. Okay, so that's how, like in the direction of water, that is the downstream. In the opposite direction of the water, that is the upstream. Okay, so in that case, when we are saying that if we are trying to calculate, like the water is moving in this downstream, and if we are trying to calculate at I and we are taking the value at I plus 1, basically it doesn't make sense. The solution has not reached the I plus 1. The solution has basically at the I minus 1, and now it will reach the I and then it will reach the I plus 1, right? In that case, if you are using the forward difference, and that is if C is greater than 0, basically you are losing the magnitude of the solution. Okay, so basically you are not extracting the content from the upstream where the already the solution is. Okay, like when we are trying to calculate the at I, we need the solution from I plus 1 because the wave was earlier at I plus 1, right? So if C is greater than 0, and when you are trying to get this downstream solution, this forward method is not the correct for you. If you have this dou u by dou x is equal to C into ui minus 1 by delta x, and C is greater than 0, then basically backward difference is correct for you. Now, because you are bringing the information from your upstream to your downstream to calculate the overall gradient. Make sense?
Yes.
Yeah, thanks. Similarly, if C is less than 0, That means wave is moving in the negative direction. So basically this became the downstream, right? And this became the upstream. And this is your somewhere wave is there. And if you want to calculate this is your I, this is your I minus 1, and this is your I plus 1, and this is moving. So basically in that case, if you want to calculate at I, like you are trying to calculate ut plus 1 at I, then basically you are basically writing minus c delta t by delta x into ui plus 1 minus I at t. That would be the correct formula. And this is the forward difference. Okay. So this makes much better sense. Now, let's say in this case you had this one wave, right? If you remember about this hyperbolic problem, when where the wave is traveling in the multiple direction, like if you have this 1D problem, then wave can either travel in this positive direction or the negative direction. If wave is a 2D problem, then and if this is the boundary, then wave can either travel in this direction or this or in this direction, right? And in that case, you don't know which one is the correct. So basically, you might have to try the combination of uh, upstream and downstream such that the formula will check the uh, what I say, the direction of flow. That means it will see, check if it is plus C or it's minus C, and based on that, it will decide either it will use the forward difference or it will use the backward difference. Okay, so that's how, like, like every time the C will change. Like let's say if you are using this dou u by dou t plus u dou u by dou x is equal to mu dou square u by dou x square, right? And here u is not the constant value. This u is that variable itself. And in that case, u can be positive or negative over the time, depends upon your initial condition, but u is not fixed, right? And in that case, you have to use the combination of this forward difference and the backward difference, and such that based on the direction of C, it will choose the forward or the backward. Okay. It has a proper name in the CFD. I am currently forgetting it, but once I will remember, I will let you know. Okay.
For the equation or
No, yeah, for the equation, like, uh,
nonlinear convection diffusion equation.
no. This is non-linear.
Ah,
Like when we combine this forward and backward difference and create one equation overall,
okay.
like, like instead of having sirf only forward or only backward, we will have
The
another.
average of I plus 1 and I minus 1? Or?
No, like if you will take the average, it will become mostly central difference. Okay.
Okay, yeah.
And in that case, it will not make sense. Okay. Like it will be become little bit better, but at least like
Lakhs will
little bit.
drop or?
No. We will. That is not in the lecture, I guess. That name is not given.
Okay,
Let-
okay.
but that is a very simple name comes into when you try to run something on the ANSYS.
Uh-huh.
They give that name. Okay, we will come to that. I will try to figure out the name in my mind.
Okay.
Okay, okay. So we had tried to understand how which one is correct and which one is incorrect, and similarly, at the same time, we also understood in a different way, in a mathematical way, that why we should use the correct one. Okay, so when we use this upstream condition in our discretization of the space, we will get the little bit of viscosity, artificial viscosity into the solution. Okay, that means like if I have this wave, this is x, and this is, let's say, u, and this is my time. So over, and this is at t equal to t. Some at some other t, if it is moving and t c equal to c is greater than 0, this will not be exactly like this. It will become something like this. Some dissipation comes into the picture. Okay, and that is because of the equation itself that we can't see, but it already contains the dissipation. Okay, and in that case, let's say if your delta x is large, uh, large means, let's say I have some reference, uh, and if it is large, then the viscosity will be higher. Viscosity will be large. If delta x is small, then viscosity will be smaller, because delta x is also getting multiplied there, right? If you remember, because that artificial viscosity has the order of delta x, right? So if delta x is smaller, the viscosity will be become viscosity will, that is also positive. I mean, viscosity will become large, and if the delta is small, then the viscosity will become small. So let's say if you are using the backward difference in this case, and if your delta x is very small, in that case you will get the minimum dissipation in these areas. But if your delta x is very large, in that case, in few iteration, basically you might get something like this. Okay, so that's the basic idea. And then we will discuss about this compact scheme. Like similarly, the idea was like if I am using this CD4, not that was CD4 or okay, I think that was central differencing 4. Okay, if I'm using the CD4, the my accuracy is of order of delta x cube, right? And in that case, even if delta x is large, the order of delta x cube becomes such very small, such that the difference of having the delta x smaller, like let's say if it is delta x and it is delta x by 2, and in that case, it will become delta x cube, and it will become delta cube by 8, right? And in that case, let's say if you're like overall the solution after some time, it looks something like this. Let me draw a good picture. Like, so this is not sharp. I have not drawn the sharp. And then I am drawing the another one. A little, a little bit more. In that case, you can say this one. However, so basically in this both case, the solution looks almost same. But since your delta x is half now, so basically number of stencil in your solution has become doubled for the whole domain, right? So basically you are doing a double computation to get the same accuracy, almost same accuracy. So that's how like you do this kind of simulation, like the convergence. You check the convergence, like how much delta, how which grid is basically giving you the similar solution. If like let's say you have the grid 1 and you have the sum 1 million grid points. Okay, you get this accuracy. Like let's say you got this CD drag value of 0.45. Okay, if you have this grade 2, you thought like, okay, I will make the accuracy higher. You made the 2 million grid point. Your CD became 0.48. Okay, and again you made the grid 3 as a 6 million grid point, and your CD is basically 0.483. then basically you will go with grade 2, you will not go with grade 3 or grade 1, right? So this is a basically grid convergence study. This is called grid convergence study. Like every time do research, at least when you are doing the research, you have to show that you are not wasting the energy and you are like you are not do you are doing a sustainable research. Okay. I mean, in at like people who has a lot of money, other countries like USA, they don't, they have literally stopped doing the grid convergence study. But in India, if you are not doing it, people are going to ask you the tough questions. So are you wasting the energy or everything? Okay. Okay.
Yes.
Now we will come to this compact scheme that is implicit in space. Okay. So this compact scheme, it has a basic structure. It has it, and that structure you must follow. And that basic structure is basically alpha of phi I minus 1 dash plus phi I plus alpha of phi I plus 1 dash. Okay. And that is equal to A of phi I plus 1 minus phi I minus 1 divided by 2 delta x. Or let's call it h. H equal to delta x. Okay. This is the alpha, these are the A. So these are the two different values. Okay, and we have to find this alpha and A. So basically, if we have this stencils and we are here like at I, and this is I plus 1, I plus 2, I minus 1, I minus 2, and we are trying to find the gradient at all these three stencil at, let's say this is t plus 1 at all these three stencils. So we are going to use this, like generally when we try to find the phi 1 phi I dash, we generally use this I plus 1 I minus 1, right? If I have to use this phi I minus 1 dash, then I will use I minus 2 and I, something like that in this case, right? But when we have to when we want to try to find the gradient all of three at a time, we create a different kind of situation. Like earlier, uh, okay, one we must look into this equation. Okay, this equation that when I am trying to find the solution at t plus 1 for all I, what we are doing is that we are using the previous I, like let's say I am moving I I plus 1, I plus 2. So basically, yeah, so this is the t and this is the t plus 1. So we are dependent on all the previous solution. Okay, we are not dependent on this current solution to get this current solution. Like this t plus 1 is dependent on all the t, right? Correct? However, when we are trying to find the solution at a space I plus 1 and I plus I minus 1, we are dependent on the space at I plus 1 or I minus 1. Okay. I mean, we cannot do that. Like we have to, or we have to look into the different kind of algorithm to find that. So what does it mean is that, like, let's say I am going from I is equal to 1 to 5. So how this equation will look like? Let's call from 0 to 5. It will become alpha, and here it will become phi minus 1 plus phi 0 plus alpha phi 1 is equal to a by 2h of phi 1 minus phi minus 1. Okay. So we will talk about what the phi minus 1 exactly mean is that. Okay. Similarly, let's say if I will go for the next one, then it will become phi of 0 plus phi of 1. Here we have the dash plus alpha of phi of 2, and it will become a by 2h of phi of 2 minus phi of 0. Okay. Similarly, we can write one more. I will write, and then after we can go direct 0 1 plus phi of 2 dash, we have dash here, plus alpha of phi of 3 dash is equal to a by 2h of phi 3 minus phi 1. Okay. If, like you can see, phi 0, phi 1, phi 2, phi 3, we have this common, right? So if we will try to write that in the matrix, and let's say if I am calling this as a phi 0, phi 1, phi 2, phi 3, phi 4, and now let's say that phi minus 1 is basically the boundary condition. Okay, like let's say I have this solution, and this is the phi minus 1. This is 0, 1, 2, 3. And since I am solving in any domain X, I must have one boundary condition. Okay. And in that case, phi minus 1 is the boundary condition. Okay. And if phi minus 1 is the boundary condition, this is a constant value. And that value is, we will look into that. So if in this case, I have this coefficient of phi, let's call it dash. So I have the coefficient of phi 0 is basically 1, right? And then we have this alpha, and that is equal to, I will take the common a by 2h, and then I will write the another form here, phi 0, phi 1, phi 2, phi 3, phi 4, something like this. And then we can write what we will be left with. This is the 0, 1. Sorry. Okay. Let's say we have the 5, and plus on the right hand side we will have a by 2h of phi of minus 1 minus, just add the minus here, and then we will also add minus alpha of phi minus 1 of dash. Okay, and these are the boundary conditions. So these are the constant value. Correct? Any doubt? Okay, let's write this as a matrix as well. So this will become a vector. Now let's look into the second equation. So if this is 0, 1, 2, so it will become 0 will become this one, alpha 1, alpha 0, 0. Correct? The second equation. And it will become 1, 0, 1, and 0, 0. Right? Like 1 will multiply with, we will have a minus 1, I guess. Here it will become minus 1. Correct. So it will become minus 1, 0, 1. So minus 1 into phi 0, 0 into phi 1, and 1 into phi 2. Correct? I am talking here. Similarly, in the left hand side, it will become alpha of phi 0 dash, 1 of phi 1 dash, and 2 of phi 2 alpha dash, right? Similarly, if we will talk about the third term, then it will become 0, alpha, 1, alpha, 0. right? And in the right hand side, we will have this 0, -1, 0, 1, 0. So can you see we are getting this kind of uh, diagonal or diagonal term and the off diagonal terms, right? And that has some order. Similarly, here we are getting something like this, right? However, we know these values. We know these values, and these are the 0, 0 in this case. So on the left hand side, and we are trying to calculate this. So we can we write a into, let's say, phi, let's some write some psi dash is equal to b into psi plus c. Can we write? And these are knowns. So we can simply write a into psi dash is equal to some k. And psi dash is a matrix, a vector. So basically, psi dash is equal to a inverse k. And this is what basically you solve in any matrix like ax is equal to b, where x is equal to a inverse b. Either directly you can solve using this, you can try to find the value of a inverse, or you can use the different kind of matrix solving methods. Okay. In this case, our matrix is not very complex. Okay. The matrix has the we have this diagonal terms and we have the one of diagonal terms, the others are zero. So to solve this kind of uh, uh, matrix that has these two terms and others are zero, we use this called Thomas algorithm. Why we use this? Why can't we simply take the inverse and calculate it? Because let's say if you are solving solver of this matrix and the matrix size is 1 million cross 1 million. In that case, you cannot calculate the inverse of such large matrix. Okay, and in that case, let's say even if you're able to calculate it, the time it will take to calculate such large inverse is way too high, and in that case, the solver time will be very high. Solver time will be very high. So in that case, since we know that our matrix is very simple, we can do some kind of substitution and manipulation. Like let's say, if I am here, if I am starting from here at the end, I will left with 1 here and the alpha here, right? And then I will have some value here. So let's little bit talk like alpha pi n minus 1 plus pi n is equal to some k. Okay, and then it will become basically right. Am I correct? Uh, yes, I think we are going right. Yes. Similarly, we will have this here in this case. Uh, we have started from this top, so we will live with this one, right? Mm, just I am thinking at the bottom, right? At the bottom, we will get two values or one values. I think we will get the one value. Okay, so we will get one value. We will use that value. Like we will get, let's say, I am getting this value pi n equal to some k, and then I am getting alpha into pi n minus 1 plus, okay, plus alpha into pi n is equal to k1, let's call k2. So basically what I will do, I will substitute the value of pi n here and I will calculate the pi n minus 1. Okay. Similarly, I will go little bit above and I will keep substituting it until we will reach the top. And similarly, I will be able to find the values of all these dash in this case. So basically, these are the dash. So these are called the substitution and addition uh, kind of method that we use in this case. That is called the Thomas algorithm. And now, so basically what happens? So basically we try to substitute from the top to bottom and then we try to add it to get the value. So this kind of methods are called the sequential method because you cannot directly get the value here. First you will get the value here, then you will get the value here, 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 here. Okay. So these are called the sequential method. So what does it mean by the sequential method is that are you aware about this parallel programming?
Yes,
Yeah, you know, right? So
yes,
So, so basically, when you have this some kind of sequential algorithm, you will not be able to get the speed up, right? Like in general, you do the vectorization. Like let's say if you have a matrix A and that has some number of n number of element, and you have the matrix B and that also has an n number of element, and you have to get C that is equal to A plus B. So basically, you add each elements at the same time. Right. So basically, if you are using the sequential computation, then like you will take in se- in sequential computation, you will take the in clock time, right? But if you have when you are doing the sequential, basically means you are doing the addition one element addition at a time, okay, and that is taking the one clock time. But let's say if you have five such computing unit, then how much time you will take? You will take n by 5 approximately, right? Because you are doing the 5 computation at a time, then you are doing again 5 computation at 1 clock time, so you will take n by 5. And if you have a n such computing unit, then you will take n by n, and basically it will exactly 1 clock time, right? So basically this is what the parallel computing and the MPI and GPU computing comes into the picture. Like if you have multi-core CPU, so basically you can use multiple CPU at a time to get your vector additions faster. Basically all this CFD, at least finite difference and finite volume, generally has proper packed computation of these arrays and the vectors. And in that case, you can directly use the parallel programming efficiently. However, if you are using this finite volume, you are using this triangular mesh or this different kind of mesh together. In that case, using this like you can do this parallel computing, but it becomes a little bit inefficient. Okay, but there we also do it. It's not that we are not using it. All the answers is basically finite volume itself. And however, if we are using the GPU has this called threads. The same thread name is also available in the CPU, but in the CPU it means a different thing. It means that you are trying to run the two program within a one process. Means one CPU will try to do the two work at the same time because they have the two threads. Thread was is basically a proper software kind of thing. It's not a hardware. It doesn't mean that they have the two computing unit within one. It is just that they will try to find the some time in between and they will try to, like if they have some lag time or some other time, they will try to do two things within one process. Okay. However, in the GPU, threads means like let's say if it has 10 threads means it has a 10 computing unit. Okay. And so similar, like in the current GPU is like A100, 800, Blackwell, and the current name the latest one name I forgot. But those have the millions and billions of these threads. Okay, and those are built to solve the matrix vector and arrays very efficiently. So you can basically you can parallelize your code in these threads, and your code will run like 100 times, 500 times, 700 times faster in the GPU. So basically you are saving, like, let's say if you are using 64 core CPU, and if your runtime is 1 hour, and if you are using 800 GPU, your runtime is 30 minutes. And let's say if you are using Blackwell, let's say I'm not sure B200 or B100 is there or not. Let's say B100, B100 GPU, and your runtime is around 15 minutes. In that case, basically you have saved your 45 minutes, right? But that is a very cheap kind of negotiation. However, like when your grid is basically of order of 100 million, in that case, this 1 hour will extend it to 4 days, something like this. And in that case, this will extend to 1 day, right? So now you know the difference. You have said 3 days. So that's why you need this kind of GPU programming. Yeah, that is a very different topic. But yeah, so
Uh,
we
can I
understood.
ask something?
Yeah, yeah, go on.
Uh, is ANSYS able to do parallel processing properly?
Yes, in
Yes.
general, like because we are using this unstructured mesh, and the unstructured mesh, let's say if you have this parallel license, like I think SPC license we call it, I guess, in the ANSYS. So when you
Yes.
are using like 20 core, 40 core, 60 core at a time. So what happens? They use this software called Metis. I'm not sure they are using currently. This like what happens? Like this, let's say this is you're doing this flow over the cylinder, and you have this complex unstructured mesh, right? Let's say some kind of like they are getting in that case, and let's say you have a lot of points here, and let's say and you are trying to say like I will use the two core, then maybe it will efficiently convert this mesh into two parts, something like this. But let's say if you say, okay, I will use three core, then it will try to figure out, okay, let's do some part here, some part here, something like this. And they are not very straight. They will be something like this. Okay. They will try to find out the in the different cores. Okay. If you are using the 16 core, then let's say it will try to give some point here, it will create a small zones for each core. Okay, and these zones are not very straight. Okay, and and also that each zone doesn't have their same number of nodes as well. Okay, so and this is done by this Metis divides the zones for the each core. Okay, and then this is how the other cores are has been divided. That is the one thing. The second thing is like when you do the parallel computation, you do the one thing is the computation, another thing is the communication, right? Communications means this is your core 0, this is your core 1, and this is your stencils in the x direction. So, and this is also a stencil. So what happens when you are trying to calculate something here, and you need the information from core 1, so you are trying to communicate the information from core 1 to core 0. Similarly, when you are trying to compute something here, and you need the information from here, you are trying to communicate the information from here to here, core 0 to core 1. Let's say both has a different memory, like it has a memory 1, it has a memory 1, and it has a memory 0. So their information are in the two different memory. So their memory are exchanging the information, and these informations are done through the call the memory buses. memory buses. And these have their own, what I say, like own capacity, like how much data they can travel in one clock time, let's say, or in some computing unit, some time. And let's say if your let's say your computation is doing like 100 computation in 100 computation per clock time. However, since there is exchange of data between the core, this exchange of data takes, let's say, 4 clock time. So what is exactly happening is that even though your computation is faster, but since you are exchanging the data and since you want to do the computation here, you will have to wait for the data to come from core 0 to core 1. Okay, or core 1 to core 0. So in that case, what is happening? Your communication time has increased. Communication time is much larger than the computation time in some way. So overall, your computation time has increased twice, in this case, the fourth time. Okay. Similarly, so the one thing you asked earlier, so I'm coming to that point now. Like, let's say if I am using 30 core, 50 core, or 60 core, and if I am using like, let's say I have a 1 million grade point, and I think like 10 core is enough, and I have ran the 10 core, I checked the time, like let's say I ran the 100 iterations, and I checked the time for the 100 iterations for the 10 core, and then I stopped the simulation. Then I tested the same simulation with 5 core and for a 100 iteration, and I checked the timing. And if I am seeing that the timings are same in the both cases, then there is no point of running on the 10 core. You understood my point, right? Because the communication overhead is coming into the picture, and you are not getting any benefit of adding 5 core to your simulation more. Okay, so
Oh, okay.
whenever you are doing the simulation, you should not blindly put the number of cores. You should do some checks, and these checks are like testing for the different cores, different number of cores, and noting the timing. And if you feel like now you are not getting any improvement, or like let's say if you are using the 32 core and you are getting some k time, and if you are using the 64 core and you are getting 1.2 k time, so basically that's not worth it. At least you should give, sorry, you are getting 0.9 k time. At least if you are not getting 0.6 or 0.65, like let's say if you increase the number of core twice, ideally your timing should be half, right? But if it is 0.9 or 0.95, there is no point of making such large number of cores. At least it is should be 0.65 because the communication is coming into the picture. So this 0.15k is the communication, right? Ideally, it should be 0.5k, the timing, right? So these are the things like since you are doing the research, you should know before putting the simulations. Okay.
Yes.
Sometime,
Okay.
sometime there is a thing like you get the computing hours from the different like Amazon or Amazon Cloud or something like that, right? So if you are not using those efficiently, like computing hour is also dependent how much number of core you are using. Like let's say you have your own GPU, you can waste all your time, energy, it's fine. But many times these computing units are sold by the government or any kind of private institution. And in that case, these kind of checks are very important. Okay. Yeah.
Okay. Thank you. Thank you for detailing it.
Yeah, yeah. I thought like this is a very important like I come in my lab and there is a sarcasm written by my professor how to waste our time in CFD, and in which one of the joke is that do blind number of CPU cores and waste your time for the next 1 month, and after 1 month you came to know that okay, you could have done that same thing in 10 days or something like that, or you could have
Yeah.
saved some computing units. So okay. So
Yes.
yeah, so yeah, yeah, so okay, now we have talked about this one, alpha and a, but we don't know the value of alpha and a. Okay, so how we will do this? We will basically expand this. Okay, and we will try to match this, like this is our formula, right? Yes. Yeah, this is our formula, right? So we will expand this, and then we will try to find the common phi I minus 1 or phi I plus 1, like, and then we will get two, three equations. Since in this case we have the unknowns alpha and the a, we can directly solve for alpha and a, right? Because these are the derivative, we will get the expansion of that, right? And the Taylor expansion. Taylor expansion are always for the derivative, right? So do you understand what I mean?
Yes. Yes.
Yeah. So once you will do this expansion, you will get these common points, and then this will become the coefficient, and alpha will become the part of these linear equations. You can solve those linear equation, and you will get the value of alpha and a. Okay. You can also prove one thing, the accuracy of these things. Okay. Like once when you will be doing it, you will get the coefficients, the order, right? Like uh, when you will get the value of alpha a, you will also get these extra terms, right? That will not get cancelled. And in that case, you will say the accuracy of your order. Okay, since we are using this alpha I plus 1, I minus 1, we are at least using three stencils, right? So in general, when we were doing the central differencing, we were getting the second order accuracy, the central differencing. However, if you will use the same second three stencil, you might get the third order accuracy in this Pade scheme. So you should check that. Okay. So
Okay.
yeah, actually this is a fourth order accurate. This this is fourth order accurate. We are only using the three stencil and still we are able to get the fourth order accurate. However, we were using the CD4, we were using the five stencil, then we were getting the fourth order accurate, right? So in that case, the compact
Yes.
scheme is little bit beneficial. However, the disadvantage is this matrix solving. Okay, because this is a sequential and this will take longer time to solve it. Okay, yeah, but okay, I'm not sure I explained that. Yeah, so when we were using this this explicit scheme, mm, this one, generally we go for the two iteration. Like one of the iteration is like correcting your own solution. Like let's say I'm going from t equal to delta t to t equal to 2 delta t. So this is the one iteration, like okay, you are going from delta t to 2 delta t. Okay. However, within going from delta t to 2 delta t, you go for multiple sub iteration for the correcting the solution within that delta t. Okay. And those are called the iterative methods of I forgot the name, mathematical name, but yeah, I will have to check. However, if I am doing this simply this matrix kind of method, then we don't have to go for all the sub iteration of correcting the solutions because you are getting the solution through directly the matrix. And yeah, and these metrics are called the TDMA, tri-diagonal matrix algorithm. Okay, because we have this diagonal term and two off-diagonal terms, so tri-diagonal matrix. Okay, and that is also called Thomas algorithm. Okay. Okay. Now we have like okay, earlier we were talking about okay, all the delta take x delta xi for I is equal to 1 to n are basically equal to delta x, means all of them are equal. In that case, our algorithm was working perfectly fine. However, if the delta xi is for delta xi is let's say 1 is equal to delta x2 not equal to delta x3, then we have to do the little bit changes, right? Like instead of so what we will write is that like in that case we have to simply like what you can write simply the formula will be the same. However, the how you are calculating the iteration will be the different because let's me write ui t plus 1 is equal to ui t minus c delta t by delta x I into u I plus 1 t minus ui. So basically here this delta x has been changed to delta xi. Okay. And every time for all the instances this delta xi will change. Okay. So only this will become a new change. And since if delta xi is delta xi is small, then this will become large. And if this becomes large, there is a chance of instability. And that is instability is calculated through this uh, one Nyman method. Nyman method. Okay, so uh, let me check if it is available in this lecture. Or yeah, professor has only given the values of this C delta T y like generally if you are using this backward difference and if you want your solution to be stable, your C delta T x by delta x should be less than always half. Okay. So there is a proof of it, and that proof comes from this one Nyman method. Okay. Where you write u I n is equal to psi to the power n into e to the power I k delta x. Okay. And then like then you use this kind of uh, formula directly into the your discretization, and you prove that for stability C delta t by delta x should be always less than half for the backward difference. Okay, you can prove it. Okay, and for the forward difference, you will find that C delta t by delta x will be always greater than 1, and that is basically the forward difference is always unstable. Okay, that we have already seen earlier, like in different ways. So I would like you to find this one Nyman method. Like I already told you what you have to do. Like when you will have the t, you can simply write n. If you have t plus 1, write n plus 1. If it is I, write delta x. If it is I plus 1, then just write k plus 1 delta x. And at the end, a lot of things will get cancelled, and at the end, you will get the value of c delta t by delta x as some value. That will tell like if the delta x should exist or it should be, then you will get some, like whenever you try to find some relation or find some criteria, you give a boundary, like this should be my boundary, and on that boundary, that is the boundary, the stability, on that boundary you will get this the value, like, and this is also called the CFL number. Okay, current Frederick Levy CFL number. Okay, uh, and if you are using this uh, mu dou square u by dou x square, there you will get a something called C delta t by delta x square, and that is called the Fourier number. Okay, and that should be less than 1. You can prove it. Okay, I would like you to prove it. If you don't, let me know. Okay, and that is also available into this PDF that I have provided. Okay.
Okay. This week's PDF or
Yeah, this week PDF.
okay.
Okay, let me check what else is available in this lecture. Yeah. Okay, I have not explained you the central difference, right? I would explain the fourth order central difference, but not the second order, right? But it should not be a problem, I guess. Like, let's say if I have to discretize dou square u by dou x square, what will you do? Basically, you can write dou by dou x of dou u by dou x, right? Now, what you can write? Let's say if you are writing dou by dou x of dou u by dou x will become ui plus 1 minus ui by delta x, correct? So now you are saying 1 by delta x of ui plus 1 by dx minus dou of ui by dx. So if you want to do the forward differencing of this one, you will write, basically this will become delta x square, and this will become uh, ui plus 1 minus ui by delta x minus ui minus 1 by delta x, and this will become something like half of delta x square ui plus 1 minus 2 ui plus ui minus 1 by, okay, already I have taken this delta x square, so basically, right? So if you want to do the discretization of second order, you can do something like this. Perfect? Any confusion?
No, nothing.
Yeah. Then let me check. There is a call of transformation to say that the Burger equation has this non-linearity as well as this diffusion. So this non-linearity, basically, let me give you this example. U dou u by dou x, dou u by dou t. Okay. So what does this non-linearity does? Like, you are a fluid person, right? So you know the non-linearity creates the
Yes.
scale into the solution. Non-linearity creates the shock into the solution. Shock means the discontinuity. So what is happening basically? In this case, when I am moving in time, this term is creating the shock, and this term is basically removing the shock, basically dissipating the shock, creating and dissipating. So there is basically a competition between this shock creation and the dissipation, and that dissipation is dependent on the value of mu. If the mu is small, the shock creation will be dominant and you will get sharp result, something like this. But if the dissipation is higher, you will get something like this. Like, let's say this is your initial condition, something like this, sine, and this is equal to 0, and you have this So what is happening? Basically, this is the view, right? And this is your x. So basically, your velocity is 0 here. So this is not going to change, right? Because the wave velocity is 0. So this will always remain here. But here the wave velocity is positive. These are the positive, these are the negative. So it will try to move into the right direction. So it will try to go here. So basically, it will become something like this, right? Because and this will try to go into this direction. So basically, it is trying to create this shock. Okay, this term. However, this term will try to dissipate it. Like this will try to create something like a very sharp value. But since this is available, this will try to dissipate it. So basically, this call of transformation is telling the exact solution of any initial condition, and then after you will try to get the solution from this numerical method, that is the discretization method, and then you will be able to compare the solution with your correct solution, the analytical solution for the nonlinear PDE. Okay, so again, the one thing I came into my mind is that the only equation, nonlinear equation that you can solve the analytical solution is this Burger equation. Okay, that's why this Burger equation becomes a very important part in the CFD to understand this dissipation and this nonlinearity and understand what is a good discretization means. Okay.
Yes. Okay.
Okay. Let me check what else there. Okay. And then there is something called the implicit in time. Mm, and that means, okay, I will come to that. Okay. Generally, like let's say I have this again equation dou u by dou t plus say dou u by dou x is equal to 0. So what I told like ui at t plus 1 is basically ui at t minus c delta t by delta x of ui at t minus ui of t minus 1, right? So I am saying that when I am moving forward in time, to get the value at t plus 1, I am using the solution from the time t, the earlier time, right? However, if I say that I want to get the solution at t plus 1, but I want to also use the solution from the t plus 1, what does it even mean? It means that I don't know these values because this is what I am trying to calculate, right? And in that case, the problem that we were solving easily earlier is not the same problem anymore. The problem has changed, and let's call this as lambda. So what will happen basically? Uh, you will get this kind of uh, solution. So basically, it will become 1 plus lambda of ui of t plus 1, right? Plus lambda of ui minus 1 of t plus 1, and that is equal to ui of t. Correct? Any problem? So this has become positive, so this will become negative. Yeah. And now, again, since you know this value, because this is all the previous time and this is the current time that you are trying to solve it. So basically, you will get this tridiagonal matrix or this diagonal matrix, something like this. So one will come in the diagonal, and that one will come below the diagonal, basically here. Okay, and that will become something like this. Okay, so basically you are getting Ax equal to B kind of problem, the matrix problem. So again, you are going to solve some kind of substitution method. to get the solution. So this is called the implicit method, implicit in time. Okay. And then there is a scheme that is called Crank-Nicolson. So what it does, it also does the exactly same thing, but it also has this implicit explicit term as well. Like so, basically, it will become ut plus 1 is equal to uit plus also minus lambda by 2 of implicit term minus lambda by 2 of explicit. So this will become implicit and this will become explicit. So what does it mean is that this will become ui t plus 1 minus ui minus 1 t plus 1, and this will become ui t minus ui t ui minus 1 t. So basically you know this part, right? You don't know this part. So this will become something like this earlier, but 1 plus lambda by 2 will become here and lambda by 2 will come here. And the other part, and earlier in the B we had this, so we have this other as well. And this will basically improve the little bit of accuracy. Now, so does it has some of the thoughtful process or it is just random? To be honest, these are very random. Like you can test your like very random. It's very random. Random doesn't mean a negative. Very random mean is that you can have a process to figure out your own discretization scheme, and you can create your own discretization scheme, but you have to compete with the previous methods. What does it mean is that, like let's say you got your own discretization scheme for some PDE, you got the solution, you checked the accuracy, and you also checked the how much time and how much the computing power you are taking. Okay. And then you have to basically, let's say you are doing research and you have got your own discretization scheme, and you told like, okay, even if I am losing some kind of accuracy, but my computing time has improved by 500%. Then basically that's your research. Now you have a paper, right? And now basically that's your discretization scheme. Okay, so that's how these things come into the picture. Like let's say if you are doing some kind of direct numerical simulation, when you have a billion nodes in your simulation, and then you are doing the time dependent solution and such that your delta t is very small, like 10 to the power minus 3, minus 4, even minus 8. In that case, basically you are running a simulation of for multiple years. In that case, if you are able to get your similar simulation, similar accuracy, almost like you are losing some accuracy, but overall your, let's say your statistical unit, like if you are taking the average and you are not losing the average, like let's say you got the solution in 1 year and you took the average of your solution over the time, and average, let's say at some point your average is 1.05, like let's write something 2.513. Okay, you created your own scheme, you got the solution, let's say 1 month, and you also took the average of your solution over the time, and you are getting 2.483, 2.487. You don't bother to get this. You are happy with, you should be happy with 1 month. Okay, so that's the creating your own scheme and finding what is possible for you and what you can afford, it means. Okay, and if you are getting that kind of timing improvement or is accuracy improvement or both of them, That's really great. Okay, into the computational background and for the computational people. And these things are literally like you can experiment, like you can randomly sit with your pen paper and randomly derive a very high order accurate discretization. But you will find that you are losing the 10x time. Then at the same day you are really doing some kind of applied research. You will never use your own research, to be honest. Okay. And then there are similar like the leapfrog scheme, Lex Frederick, Lex Vandroff. So like let's say if I have this leapfrog, it's like ui of t plus 1 is equal to ui t minus 1 minus c delta t by delta x of ui plus 1 n minus, that is the t. Basically, let's call it 2 delta x. Okay. So basically, you are saying that you are not moving, you are leapfrogging in time 2 delta t rather than using the only delta t. So that's what basically this is also called central in time and central in space. Okay. So basically, you have a 2 delta t, so 2 get cancelled basically. Okay. So this is called central in time, central in space. Then you can have a Lex Frederick scheme that is called forward in time, central in space with averaging. So basically it is like uit plus 1 is equal to half of ui plus 1 at t of ui minus 1 at t, and the other part like central in scheme. So basically is c delta t by 2 delta x ui plus 1 minus ui minus 1 at t. You can see these are just experiments, right? You can go and find the accuracy. It doesn't really matter, to be honest. It matters in the long run. I'm not even. I would not say that would be actually quite positive thing to tell. Like, but when you will try to go for this good enough scheme into this complex uh, compressible flows, then maybe these things will make sense. But right now, these things literally doesn't make sense. To be honest, you will say, okay, these are very random. Then there is a Lex Vandroff scheme. So this is basically forward in time and central in space with the numerical diffusion. Okay, so it's basically forward in time, central in space with numerical diffusion. So it is basically uit plus 1 is equal to uit minus c delta t by 2 delta x ui plus 1 t minus ui minus 1 t plus c square delta t square by 2x square ui plus 1 t minus 2 ui t plus ui minus 1 t. So basically you are adding a diffusion on your own. You can see this is the dou square u by dou x square, right? With delta x square here. So basically you are saying that this scheme has negative viscosity. So basically you are adding some positive viscosity to remove the instability. Okay. So you are adding the diffusion. So like let's say this is your wave, and since you are getting this kind of solution after some time, but since you have added the diffusion, this will slowly become okay. Let me use, so This is my initial solution. This is my solution due to the instability. But since I have added the diffusion, this will become something like this. So what is happening? Basically, this spurious wave that is coming into this red color, those are getting diffused. However, if they will not get diffused, after some time they will blow up. So basically, this diffusion is helping to stabilize the solution. Okay. So this is the overall idea of this week. So let's see some programs. My screen is visible.
Yes, it's
Okay, let me do it again. Oh, sorry. Okay, let me try again. Oh, I think I have not used the Python in my computer for a long time. So yeah, it needs some installation. Okay. Yeah, I was just trying to remember this upwind word. I was using upstream, downstream, and everything, but I could not able to tell the word the upwind basically. So upwind is like you have a scheme where if there is if the C is positive, then it will use the backward differencing, and if C is negative, it will use the forward differencing. Okay. So in this case, if I'm assuming that my C is positive, I am using the backward differencing. So right now, uh, like okay, let it install. I know. I think it will take time. Should I upload it on the Jupyter? Yeah, let me upload it on the Jupyter. Okay. I mean, sorry, Colab. Mm, Yeah. So we are using the CPU for right now. Or should I be use? Okay, let's use the CPU. Okay, let's run this. It is still connecting. Yeah, it ran. Okay, so you can see that I am defining the initial condition. Initial condition is basically this line, this dash line that tells that if u is greater than 0.5 and less than 1, its value should be 2. So basically it's greater than 0.5 and less than value. The initial condition has been defined. And then after I am using this discretization. So this is basically time and this is the space. I mean the solution in a space, and over the time the history is basically updated. And you can see that I am using one. I'm starting from 1 and going it to 0. Okay. So basically this is the backward difference. If I have to do it the forward difference, what I will do is I will say that uh, I will say it like I will start from 2 and I will call it 1. I think we will get some error here. Hopefully. Yeah, I guess. Okay. Let's call it 0. No. So we are calculating for the 1, right? So we have to get from the 2. Okay, correct. So now again run it. Are we getting error? Yeah. So what we have to do is that we go till -1. Okay, now these are the programming things. Okay. You can change the condition here. So it will go till -1. Let me check. Let's do it again. I think we have the error again. It is going from 1 last value. Okay, let me improve the command that. Okay, let's copy this. Backward difference. Forward difference. We will comment this one out. And then we will update this one. So idea is to update this one. Okay. But we want calculating from 1 to, okay, so it should be 2. So let's do it 2. And let's go for the 1. So let's say for the till -1. So let's see what happens till -2. 1. So what is happening? Okay, let's see there. Let's keep the cursor here. So it will say, okay, it is not telling me the unit. Okay, so let's call it -2. What? Let me correct it with the blender. Basically, I want to tell you that when c is greater than 0, so you can see the instability into the solution. Let me check. Yeah, it is already there in the bottom. Okay, but different kind of instability. Oh, oh, got it. Yeah. So basically this one. Okay. Are you there? Okay.
Yes, yes, I.
Yeah. So let's see. So what I was saying is that, so I have kept the lambda to the value of 0.2, that is less than 0.5, and I have used the forward in time and backward in space. So basically I told you like there is a diffusion available, right? For c greater than 0, and we can see the diffusion here in the code. If I am using the lambda greater than 1, you can see also become infinite, like you can see the blow up, right? At this point here and here, the two blow ups are coming. Now let's say if I am changing the sign of the c less than 0, and then my forward difference should be stable and the backward should be unstable. So when I am doing this backward spacing, like I am running the two cases, the forward and the backward. In the case of backward, the earlier that we are seeing, but there the C was positive. So let's see if we can do something about this one. Here we have this lambda. Where is the C? Okay. Yeah, this is a perfect example to test it. If scheme is auto, scheme equal to backward differentiation is forward. Okay. If C is greater than 0. So let's say if backward differentiation C is less. Perfect. Now C negative. C negative is, let's make it positive for right now, and let's see what happens. Command Z. Okay. Now let's make it positive. So what is happening? The forward in time and backward in space is also the correct solution. By why it is showing the correct? This should be unstable. Okay. Okay. What is the first plot? Let me check. X. Okay. Sorry. Yeah. So basically, this is what I wanted. Let's write it auto. AUTU. Yeah. What we want? Forward displacing. What is happening? Let's see. Okay. Okay. The scheme is so this is a C, and I told like if C is greater than 0, use the backward referencing as auto, else forward. I want it the other way. What is scheme is backwards. Yeah, got it. Now you can see that the instability has gone. Okay, so once we change the like we have this let's write it negative, doesn't matter. Yeah. So what I did, I told like, okay, if C is greater than 0, and if we are using the forward scheme, I should get the unstable solution, right? And I am getting the unstable solution. For the forward in time and forward in space for the C greater than 0. Forget about this because you were earlier written it. But for the C greater than 0, we are getting the stable solution, right? So this is what I wanted to prove it. And this is the shock formation. Not this one. Yeah, forward in time and central in space. Yeah. So again, we have to look into the stability, that is the C delta T by delta X square. Like for the lambda of 0.375, we could get a very smooth solution, right? But if for the lambda of 125, we are getting this instability. That is not the correct solution. So the code is like we have this central differencing, and then we have this t, and this is the t plus 1, and we are applying the boundary condition at each step too. So let me explain this code to you directly. Like I am solving this diffusion equation. So this is the n plus 1, this is n, and this is the this term where lambda is basically u delta t by delta x square. And for the one Neumann analysis, if we want the stability, the lambda should be less than 0.5. So these are the uh, this is a function, and these are the arguments. Okay, in the Python terms, and then we are creating this stencil from 0 to nx minus 1. So nx will be decided when we will call this one. Okay, nx is like number of stencil I want between. Let's say my domain is from 0 to 1. Okay, right now we have the domain from yeah, 0 to 2. So basically in between 0 to 2 I have the total number of stencil of nx minus 1, and the dx is basically 2 by nx minus 1. Okay. At- and then I am creating this all the value of u, like n, nx, right? Where is the nx? So wherever it is called, we'll see. So nx is here. So nx we have this 51. Then we have the nt number of time, we have this 60. Like for let's say how much time we are solving. We are solving for we have this dt stable. Okay, we can figure that out for right. So basically our dt is 0.006 and total number of steps is 60. So basically you can multiply it and that will be the total time. So basically 0.036. Okay. And the unstable one, we have the 0.02 into 0 into 60. So it will become 1.2 second. So when we say that, okay, our time step is larger, and in that case, our lambda is larger. If our time step is smaller, our lambda is smaller. And in that case, for the same delta x, we are getting the unstable solution. Okay. Similarly, here we are solving this uh, Berger equation, and in this case, our u is positive. So we are getting a very good solution for right now. And if we will use this comparison of this call Hopf for this equation, the what is the initial condition here? We have to check the initial condition. Mm, we have this again. What is the initial condition? High Berger numerical u exact is okay. So basically, whatever the there should be some initial condition. We are discretizing it, and then we are creating this phi, then we are finding the exact expression, we are exact function, converting it into the function. So whatever we will give this xts new s, we will get the solution. Okay, okay, got it. So what is happening basically? So we have got a exact solution for any sum for phi given this. Like this phi will give at, like if we will give the t equal to 0, we will get the exact initial condition from this phi. And for that phi, we are getting some solution. And for that solution, we are we are getting them some solution, and there is no, basically you can say there is no effect of nonlinearity on that solution. However, if we are doing this discretization and we are getting the solution, we are getting a little bit of different result. So what is happening is exactly is that since there is no effect of uh, what I say, the flux term, the non-linear term. So the only the viscous term is coming into the picture. However, we are getting an extra viscous term from the numerical dissipation. Okay, and that effect is basically visible here. You got the point? So what is that? Like we are keeping this initial condition such that there will be no effect of nonlinearity. That means the solution will not change with time. Okay, and in that case, and like only the solution will change because of the viscosity. And since there is a viscosity available into the numerical as well, we are getting a little more dissipated solution into the CFD compared to our exact solution. Okay, and you can see these things. Okay, similarly, you can check this Lex Vandra of. So if you remember last thing we talked about this Lex Vandroff, right? I told you even if we have this non-linearity and this spurious wave that is coming to the picture, we have this extra viscosity that is added. That viscosity is basically stabilizing the solution compared to this leapfrog. It has also this little bit of what I say uh, mm, spuriosity, but this is more dissipated. Okay, so in general, what will happen? This spuriosity will never grow a lot such that this Lex Van Droff will become unstable in longer iteration compared to this leapfrog. And since Lex Frederick is the first order, and that is what we were using in the Lex Frederick. Do you remember? We were using this averaging of the solution and the central differencing. But this is not even the central, this is the first order central differencing. So basically this is creating this viscosity into the solution, and that's why there is no spuriosity. So what you have to do is basically you have to test this. You have to run it, you have to like check the initial condition differently, like give the different initial condition and run it. And then you will be able to find the solution in a different way. Like let's go here in this first example, instead of minus, just do the plus. You can, okay, what is happening? Yeah, okay, and let's run it. You got the unstable solution, right? Because you suddenly change the direction of C. And you are saying that for the C less than 0, the backward in space is basically unstable. The forward in space will be the stable one. So that's how you can see things. Okay, and it has become stable, I guess. Yeah. Similarly, these things are available. And then we have this Pade scheme. And in the Pade scheme, this is the second order. Okay. Very Pade scheme. Okay, the Pade scheme is not given here. Okay, I will add the person because these are the only the central differencing second order and fourth order. And you can, if you will look into this one, you will see that the second order is a little more dissipated. So you have to zoom here. However, this is quite visible. So let me do something. Okay. EL2 dot y limit and I will keep the value limit between 0 to no 2 to 3.1. 2 to 3.105, let's say. Yeah, you can see it, right? You can see the dissipation is more visible in the second if, although like both are stable, but because the order of accuracy is second order, you can see the accuracy matters. Like when you are doing the complex simulation and or for a long time, these accuracy matters because this inaccuracy will grow over the time, and after some time you will get the very different solution that you expect. Okay, so this kind of accuracy really matters. Oh, okay. We have this. Okay. In this case, we are directly using this AX equal to B. However, how much we are using the 51. So our matrix size is 51 cross 51. But let's say if I will use this as a 51, 5001 cross 5001. Suddenly this linear solver AX equal to B, finding this inverse will become very complex. The number of computation will exponentially increase, and and it will take much longer than you know. Oh, still quite fast. Let me use it to agent. So I just wanted to tell you the difference of timing. Yeah, yeah, the session has crashed basically. So it was too much for the collab. So okay. So in that case, right now, like trigonal system, right? But trigonal system can be directly solved using Ax equal to B. And in that Ax equal to B, the A is basically we have to solve X equal to A inverse B. And A inverse, we have to calculate it using this linear algebra solver. However, this is not feasible if your matrix size is very big. Okay. So this is what I wanted to tell. And you can see that the compact scheme is way more accurate. Means the error is way too low. Like let's say if you are changing the delta x, like let's say if your delta x is order of -2, the error is order of -6. That is way too accurate. If it is 0.1, the order of accuracy of -4. This is what it is basically. And if so, overall, this compact scheme is much accurate. Okay, compared to central differencing. However, this Ax equal to B, this will matter in the longer run if you are using a very large grid. Okay, so yeah, this is for this week. I think today's week was quite simple, not very harsh in the term of knowledge or information. Yeah. Mm. Any question you like to ask?
Uh, no, as of now, nothing also.
Yeah, so today's was quite normal week, and I think since you are traveling, that's also good for it. Yeah. So thank you for joining
Yes,
and
that was helpful.